Jacobo Aguirre, he's actually a group leader, and he is joining us from Madrid in Spain today, from the Center for Astrobiology there. So which university it is, Jacobo?
It belongs to CSIC, which is like the public system of research in Spain. So it's not a university. It's a research center.
It's a research institution. Very, very nice. Thank you. And Jacobo will talk today to us about network science environment and prediction of transitions towards complexity.
Can you see the PowerPoint now?
Astrochemistry. Okay, yeah.
Okay.
Wonderful. So thank you, Jacobo, for actually joining us to speak under these unexpected circumstances. So yeah, take it away. I will keep your timing.
Let me first start thanking the organizers for giving me the opportunity to speak here. I wish you very best of luck in the future of your society. I'm sure that we will be in contact in the future. And I'm going to talk about what Rafael just said, network science and the prediction of transitions towards complexity in connection to astrochemistry. I am Jacobo Aguirre, and I am the leader of a group that we are organizing right now in Madrid that tries to join complexity and astrobiology. So we are new in not in the subject, but we're trying to do a different point of view of this difficult world. Okay, let me give you a couple of ideas of what I'm going to tell you today. We're going to present NetWorld, which is like a conceptual, if you want, or computational framework, where we want to model the evolution of different structures that can be described as networks towards complexity. These complex networks could be anything you want, but in this case, for you to get the main idea, you can imagine that they are chemical compounds, small chemical compounds. We're going to see that there's a transition towards complexity, and that we're going to describe. And while this is very important, the rules are not taken from chemistry. Actually, they're taken from sociology or even game theory. Our results are surprisingly compatible with, for example, the molecular abundances in interstellar clouds, where you know that the bricks of life were created before falling into the Earth around 4,000 million years ago. So, what do physicists want to tell you from this point of view of complexity is that even if we know that the transition from chemistry to life was extremely hard, and we are all working to shed some light on it, it is true that there are some relatively simple and general patterns that can be seen in these processes, and we like to look at that and try to find some kind of universality in these processes. All right, so what does NetWorld do? We start our simulations with N means like 30, 40, 50, something like that, isolated nodes. You can imagine them as atoms, okay? These nodes are going to interact to form complex structures, but at the same time, they can connect to other structures or be divided in smaller structures, or be divided and become again small little compounds. This is the probability of division, which is not very important, but it's important the point that it depends on the only global parameter of the model, what we call the environment parameter. Why do we want to make it so simple? Because we want to make this make it as simple as possible to see how universal the results are. Okay, I'm going to talk about beta all the time. So take home message: different beta means different environments. All right. What does it represent? For example, it could concentrate the physicochemical properties of what we are studying: temperature, radiation, the amount of interstellar dust, whatever you want. I don't mind. But different beta is different environments. So what am I showing you? I'm showing you some kind of artificial, very, very simple artificial chemistry of networks. All right, I don't want to give you really the details of how it works. If you are curious, please ask at the end, but just a couple of ideas. If you have this A network, which is very simple, and it gets close to this B network, they will connect to form C, or this one, just if each of the nodes that get connected win in dynamical importance. This is an important quantity in complex theory, in complex networks theory, but imagine that it's something local. So if each node wins something, when it connects to another node, it will do it. Otherwise, it will not. All right? This is the simplest system we could imagine. And for you to understand what the simulation means, we start, I have put here an example. You start with 20 different nodes. All right? This is an example. And they start to find other nodes and connect to them and sometimes divide. Okay? After a few steps, you have these very simple structures, but then they get more complex, then they get destroyed again, then they get more complex, and at the end, all 20 finish joining together to form, to create like a molecule, a very complex molecule of 20 nodes, and we stop there. Okay, what is the diversity here? The diversity is made of all the structures that were found in any of the steps. This is the diversity of our environment, which now will be beta equal 2.5, for example. And what is the abundance? The abundance is the number of times that each of these structures appears in our process, all right? And we repeat this lots of times and with many different betas in a cluster, okay? And so we can describe this artificial chemistry by seeing which kind of structures are going to be created. All right. The main point, whenever we change beta, whenever we change the environment, we realize that there is a critical beta in which for small betas, which means that the structures are being divided really fast, they're very unstable. And so you can only create very, very small number of molecules. I don't know, in this case, it's like 1, 2, 3, 8, 10. All right, but if beta is sufficiently large, the structures can start to grow, and it appears that we get into an exponential growth of diversity that you can see it in this first picture, and then things change completely. Look at here. For example, this is the sizes of the different structures of the different molecules that we're going to that appear in a system. For beta small, you have like 5, 6, 7, 8 different structures, but for large betas, you have even up to 40 or as many nodes as you can let it work with. And if you study the complexity, you will see that after this critical point, we either have very simple, very regular networks, like a cube, like a, I don't know, like a square, things like that, but you also have very, very complex structures. So, to get you an idea, when beta is small, you don't have a lot of diversity, but when beta crosses this limit, the number of configurations grows exponentially, and you can have either small or big configurations and either simple or very complex ones, all right? So you have a very huge universe, if you want, of structures. I haven't talked to you about abundances, and this is important. Because, I mean, you can have a lot of diversity, but we want to know which are the structures that are the most common ones. All right. Here you can see that for small betas, all structures are destroyed, and so you only have like these isolated nodes. But whenever beta start to grow, you start to find different structures, like 3 in a row, 4 in a row, 5 in a row. And in 1.5, which is this critical point, you have a cascade of appearances of structures that keep on growing and growing. And in fact, if you study the complexity of the whole system from the point of view of ecology, using this typical entropy quantity, you clearly see that at 1.5 you have a clear transition. Something happens at this place. What does happen at this environment? Well, if you paint it from a point of view that people who work in ecology love, which is like painting abundance against rank, that means this is the abundance of the largest of the structure that is the most abundant. This is the second most abundant. This is the third most abundant. Okay, and you paint it, you will see that for small betas, when there are only where there is no complexity really, these structures follow an exponential curve. However, when you cross this transition, there is a functional change, a conceptual change, and what you have is these large fat tails, and this structure, this curve follows what we call a power law curve, which means that there is a rare chemosphere, because it's not biology, so it's not a biosphere, a rare chemosphere of individuals that are not very, very abundant, but they introduce a huge diversity to the system. So I hope to have convinced you that there is some kind of transition there. All right, but you can say, okay, you're a physicist, you're talking to us about complexity, but is there any connection between reality, between your work and reality? Well, when we got to the Astrobiology Center a few years ago, I contacted the astrochemists and explained them this question, and they said, you have to look definitely into the interstellar medium, into the clouds in the interstellar medium. Why? Because there you see how it's very, very small structures, small molecules react, and the main building blocks of life appear sooner or later. And actually, they have a transition, very nice transition. Why? Because we have a real connection to our beta, because the interstellar dust in the first steps of life of the evolution of these clouds, the dust is not able to attenuate the ultraviolet radiation, so most molecules are destroyed, and you only have like 5, 6, 7 different molecules. However, whenever this interstellar dust gets more and more concentrated, there is a critical point in which the interstellar ultraviolet radiation becomes totally attenuated, and there is also an exponential growth of the appearance of molecules, and so you have also like a very nice transition to study. So we said, okay, let's try to compare our toy model with the real abundances of molecular clouds. And what we obtained is that to the right here, we have for the abundances of our model for 4 different values of beta, and here we have the abundances of the real abundances of molecules in 4 different molecular clouds. The first one, the black one, is a diffuse cloud where there are only like 10. You can see 10 different molecules. The second one, the green one, is Sagittarius. It's a translucent cloud, and this is what these people, the astrochemists, call a transition from the diffuse regime to the dense regime. Whenever you get to the dense regime, the ultraviolet radiation is completely attenuated, and you can have 40, 60, or even 200 different molecules. And we can see that not only qualitatively, but also quantitatively, our model can, surprisingly, in some sense, fit the real data, which was a good point. But then we asked, okay, let's try to see how predictive our model is. And this is something that I love about models, that sometimes they give you some information that you had not even thought of in reality, and then you look to reality and you see if things fit. Okay, in this case, in this curve here, bottom left, because I don't see if you're seeing, I hope you're seeing the mouse, but I'm not sure. I saw that the abundance of the structures that I was creating, for example, a cube, or for example, I don't know, or a square or whatever, had this kind of very simple relationship, okay, an algebraic relationship with the number of paths that gives rise to each of the structures. Imagine, which means that if there are more paths that lead to, I don't know, a square, there will be more squares than any other structures, no? And so I said, okay, let's get the real data and see how its abundance, the abundance of the real data, depend on the number of reactions that potentially can give rise to water or whatever. I went to this KIDA database that gives us the number of astrophysical reactions that potentially show them as products. And the very surprising result too here is that we also were able to find this fitting where alpha is in both cases, both in our system and both in reality, around 1, which means that, in some sense, the most abundant molecules in these clouds are the ones that are there are more astrophysical reactions that could potentially have them as products.
About 2 minutes left.
Oh, all right. I'm in conclusions, so don't worry. So the main take-home messages. The first one, we created a computational environment, absolutely abstract, where actually the simple rules that make networks connect are taken from game theory and complex networks theory. Actually, I developed them in a former work to work with sociology and with social groups. But it recreates a rich chemistry of networks with very simple reactions of these typical types. All right, we've seen that our model is, however, complex enough to show a transition towards some kind of digital chemosphere, if you want, where there is lots of very different structures of different abundance, size, and complexity. And our results agree with real data, at least in the abundance of molecules in interstellar molecular clouds, which is, of course, a very simple system. Biology is something much more complex, of course. It has our model as this predictive potential because we have found an undetected relationship, actually, between the molecular abundance in interstellar molecular clouds and the number of reactions that have them as products. And the astrochemists told me that, as far as they knew, nobody had looked at them from this point of view. And this is something new that perhaps could be used in the design of radioastronomical surveys, who knows? And final, just which is the future work, we really don't know. Any ideas will be welcome. Perhaps we could attack the potential polymerization of simple chemical compounds to work on this RNA world modeling. We could think of looking for autocatalytic reactions to help to give a new step towards biology and to see whether we can define the concepts of mutation of fitness, but this will be, of course, further in the future. We don't know yet, but we are very excited, and so thanks for everything, and any questions will be welcome.
Fantastic, really interesting talk, Jacobo. Thank you so much for presenting it, and also thank you for actually presenting it a bit outside of the planned schedule. So apologies for the problems. But anyway, let's go to the questions, and we already have the first question here on the chat. And Łukasz Tychoniec is asking, can you also predict abundances that take into account different sources of radiation, e.g., the UV flux induced by accretion flows onto protostars should alter the chemistry in the innermost regions? So you can see it in the Q&A panel on the right-hand side if you want to read the question. Okay,
so but I think I might put you in out of trouble if I try to look at that. No? In fact, we can't, in the sense that we did our best to simplify the system as much as possible. So everything should be inside this beta. Of course, we can complicate as much as we want the system. For example, our main point, all our atoms are the same. And they can connect to as many other nodes as we want. Of course, the first step would be, oh, come on. I mean, carbon has a different connection structure than, I don't know, than sulfur or whatever, no? But if we make the system more complex, then we would start to compete, if you want, with people who do artificial chemistry. And artificial chemistry is very, very well developed. And there are huge models and very, very complex models to do all these kind of things. And also astrochemical models are so very complex. I know that, I think there is a person who's going to talk about that later. So we wanted to make a toy model as simple as possible. And so, of course, we could do that. But if we started to modeling, then where do we stop? You know what I mean?
Thank you, Jacobo. So we have another question from Giuseppe Cassone, who asks, is it possible to directly relate your predicted reactions to quantum mechanical predictions for selected reactions? What about external conditions, heat, pressure, etc.?
I must say that this is the question is more or less the same. The answer as I said before. The system is very simple. Very simple. However, we have another line of research. Actually, there's a poster about that of one of my students, where we study from a much more detailed point of view the phosphorus chemical network. In that case, we are able to get real results that are being compared with real abundances. And actually, there are some some chemists, experts in quantum mechanics, that are trying to get the real values of the different coefficients that they have more or less invented, because most of them are not known. And so we're doing real predictions in that case. And so they try to, okay, we have to look at this reaction, because the reaction is very important. Then let's do it from a quantum point of view, and let's study the system. But for that, you need something which is much more connected to reality than our model. Actually, this is why I said several times, perhaps too many, I'm sorry, that we're very surprised with the results, because this started to being very abstract, but at the end, nature is so there are not so many answers for several questions. No, so universality appears everywhere, but of course you cannot ask for it too much.
I mean, a very interesting idea. So, I mean, when we already speak about quantum chemistry, how do the computational costs of your models compare to quantum chemical simulations, for example, or some other type of molecular simulation?
In this case, we use a cluster, but it's not very, very time consuming. Of course, I mean, if you want, the point is that if you want to study lots of environments, of course, the more statistics you do, the better. But the results are quite general, and you find them quite soon. Actually, we did our best not to make a very, very complex system, neither computationally nor from a point of view of inner organization. But of course, if you make it too simple, then things don't work. As I think Einstein said something like, "Do your models as simple as possible, but no more." And so we have to find the precise point, no?
Excellent. Thank you so much, Jacobo. I see that there are some more questions popping up, so feel free to answer them, reply in the Q&A section, or you can also write on the chat. We will really appreciate it, and also I think the people who ask the questions will appreciate it as well. We have to move to another speaker. Thank you, Jacobo,
Thanks
for
a
your
lot.
time. Thanks.
Thank
really
you.
Nice to see you. Wonderful.